So the first invited talk is by Francesca Toni, and I am very honored to introduce her to you. So she's a professor in computational logic at the Department of Computing, Imperial College London. She is also the Royal Academy of Engineering and JP Morgan Research Chair on Argumentation-Based Interactive Explainable AI. So her research interests lie within the broad area of KR and explainable AI, in particular argumentation, argument mining, logic-based multi-agent systems, non-monotonic, default, defeasible reasoning, and machine learning. She graduated in computing at the University of Pisa, Italy, and then received her PhD in computing from Imperial College London. She has coordinated 2 European Union projects. She has received funding from EPSRC in the UK, and she was previously awarded a Senior Research Fellowship from the Royal Academy of Engineering and the Lever-Hulme Trust. She is currently the Technical Director of the Road to Age project and co-director for UKRI Center of Doctoral Training in AI for Healthcare. And also she was founding co-director of the UKRI, the Center of Doctoral Training in Safe and Trusted AI. She has recently been awarded an ERC Advanced Grant on argumentation-based deep interactive explanations. So she has published over 200 papers. She is URAI Fellow. She has co-chaired ICLP and KR conferences. She is the current chair for Comma Conference for 2022. So she is the corner editor on argumentation for Journal of Logic and Computation. She is in the editorial board of the Argument and Computational Journal, the AI Journal. She is also in the board of advisors for KR and also theory and practice of logic programming. So I'm very happy to pass the stage to Francesca. Welcome, Francesca. So we are very excited to hear your talk on the interactionist view of reasoning for explainable AI.
Thanks a lot, Ezra, for the kind of introduction. I got tired only by listening to it. Too many things. So thanks a lot. You were very exhaustive. Ezra, can you see, can you see my slides?
Yes, I can see your slides.
I cannot see myself, so I don't know whether you see my face as well, but I cannot.
Well, I cannot see you.
So there is something wrong with the system, but I'm here. So although you don't see my face, I'm going ahead. Okay, lovely. Thanks a lot for inviting me. I'm really honored and excited by the opportunity to talk to you about this work. I'm going to start giving you a bit of introduction about explainable AI and how this is being pushed, throughout by, legislation even, and guidance and governments and companies. I'm then going to tell you a little bit about the interactionist view of reasoning by Mercier and Sperber that somewhat, in my mind, inspired some of the work that we have been doing on using computational argumentation for explainability. And I'm going to tell you a little bit about that, giving you a flavor. Computational argumentation is very much a KR product, but it kind of is also situated at the intersection with multi-agent systems and more recently, natural language processing and machine learning, in particular, with the work on argument mining. So let me start with something about explainable AI. So why are we talking so much about explainable AI? Why is it such a hot topic? There is a widespread understanding that AI can, yes, do a lot, but it needs to have somewhat the human in the picture, the human somewhat holding its hand, putting it in the words of the economists. There has been a push by funding bodies towards explainable AI. DARPA, for example, we're having a program pushing for it. There has been legislation that can be interpreted as pushing towards explainability, in particular GDPR, has been interpreted by some as sanctioning the rights of explanation for algorithmic decision making. There have been guidelines on kind of ethical uses of AI, trustworthiness of AI, pushing towards explainability. And governments, in this particular example, the UK government is pushing towards explainability. This is coming from the Law Select Committee on AI in the UK. And of course, industry is very interested in explainability. Here I'm just citing JP Morgan, whom I collaborate with, that have recently started an explainable AI Center of Excellence. So there is a lot of hype, if you like, about explainability. What is it? I mean, how can we support it in a way? Here I'm kind of putting a kind of summary given by the Arpeggio company. I think Fabrizio Silvestri pointed me to this nice summary by this company. So you can see what the landscape somewhat is like. If you want to explain a model's decisions, then you have two options. Designing the model so that it is interpretable, and these, if you are doing machine learning, amount to using logistic regression or linear model or k-nearest neighbors, decision trees, or the kind of things we do in KR, or if you don't want to use a model that is interpretable by design, then you need to decide how you're going to explain it. And you can, in general, choose a technique that is model agnostic, that works no matter what's your underlying model. Here with model, as in standard machine learning, what means some kind of, for example, classifier built from data, and some system basically that is able to compute an output. You can have one that works, whether you use a neural network or whether you use a decision tree, it doesn't really matter. Or you can choose a model-specific approach that is tailored to your methodology. So if you use neural networks, for example, you could use gradients as one possible way of explaining the outputs of the neural network. Or you can go for what's referred to as example-based, namely choosing specific data in the training data set. If you're doing a machine learning kind of method as an explanation for its output. And this includes the counterfactual methods that are so popular these days. So this is somewhat the overall landscape. And of course, if you are not interested in explaining the model's decisions, so all you can do is just look at how the model works without building a kind of an explanation for it. So let me tell you a little bit more about some of these methodologies for providing explanations, which are these, if you like, these four bubbles. So the kind of, I would say, standard kind of methodologies for explainable AI and for providing local explanations are attribute-based, rule-based, and counterfactual explanations. Here I'm giving you a kind of simple illustration with respect to a machine learning method that from an input computes an output. For example, that your credit card application has been denied. And you as a user may want to have what's referred to in jargon as a local explanation, which is an explanation for the specific input-output pair you're interested in. So if you are interested in an attribution-based explanation of the kind that Line, Sharp, and LRP, for example, would provide, I'm just throwing these names there in the hope that you have heard about them, but it's not very important that you have. They're just very popular attribution-based explanation methods. So if you are after an attribution-based explanation method, you may receive an explanation that says the card was denied because the client is credit unworthy, despite good salaries. So these are, these are explanations where features may be shown as having a positive role or a negative role in leading to a conclusion. Lime and Sharp are model agnostic methods that compute this kind of explanations, and LRP is a model-specific method tailored to neural networks that computes this kind of output. If you are interested in a counterfactual explanation, then you may obtain something like, had the client had a good credit score, the card would have been granted. So this is somewhat identifying the features that are responsible, because if different, so the credit score is the feature that if it had a different value, good instead of bad, would have led to a different output, that your card would have been approved. And this is the kind of approach that Tolomei et al. First put forward, and Wachter et al. Somewhat popularized. And finally, you could obtain rule-based explanations that, for example, uses rules of the kind: if the client is credit unworthy, then the card is denied. And some of them, like anchors, are obtained from other model agnostic methods. In this particular case, they are defined similarly to Lime. And there are ways to obtain this kind of explanations, for example, from decision trees that somewhat mirror the underlying method. So this is a kind of an overall picture exemplifying what explanations may look like in this particular setting, where we have a machine learning classifier that decides whether credit card applications are accepted or denied. There are other solutions, as the arpeggios cheat sheet said, and there are in particular advocates of using explainable models instead of explaining other models, for example, black box models, especially when there are high-stake decisions involved, for example, in healthcare and law. So Cynthia Rudin, who was recently awarded the AAAI Squirrel AI Award for pioneering socially responsible AI, is a strong advocate of this view, and is somewhat pushing in the direction, if you like, of global explanations. Your whole model is explainable, and therefore, no matter what input you are considering and what output you need explaining, you can inspect the model. All of these approaches, the approaches that we've seen so far, are somewhat not taking into account the human aspect, and in particular, whether these explanations are useful to humans. This is especially crucial considering that the humans at the receiving end of explanations may be very different types of humans, may have different kinds of expertise. They could, for example, be developers of the models. There may be clients in this particular case of the credit card denied. So there can be kind of clients of the financial institution that is using this tool for dealing with credit card applications. There can be regulators that need to somewhat push for fair and trustworthy forms of AI. And these different types of users may really have quite different kinds of expertise. So it's unclear whether a one-size-fits-all explanation, such as the one that comes with the sharp standard implementation, would be suitable for all these different types of users. Here I'm just giving an example of a sharp explanation. Sharp is a feature attribution method for computing local explanations. And as you can see, it kind of identifies the features and the role they play in sanctioning an output value for an input. So it's kind of unclear whether this could be suitable to all, but I think it's unlikely that this is going to be suitable to all forms of users of explanation. So at the same time, there is a big push within AI on having a more kind of human-oriented explainable AI. And here I'm quoting Tim Miller, his well-known survey of 2019, looking at how humans explain to each other can serve as a useful starting point for explanation in AI. So somewhat there is a drive, a push towards looking at what humans do in designing solutions that work for humans. In particular, Tim Miller pushes towards an explainable AI vision whereby artificial intelligence and human-computer interactions play a role together alongside the social sciences, which have for so long looked at how humans work. So let's look then at some kind of solution within this sphere. Let's look somewhat at what social sciences have got to say about the way humans explain. And in particular, I've been looking at the interactionist view of human reasoning put forward by Mercier and Sperber. They, of course, look at it as a theory for, if you like, human reasoning itself. Whereas, as I will argue, I am viewing it as a motivation and a kind of guidance for designing explainable AI solutions. But let's first look at the view itself. This table in Mercier and Sperber's book, The Enigma of Reason, is somewhat, in my mind, epitomizing their view of their kind of interactionist view. So they basically look at how humans produce reasons and how they evaluate the reasons produced by others. And they kind of observe with a bunch of experiments by themselves and others that humans are not very good when they produce their own reasons. They tend to be biased with a my side bias. They mostly produce reasons for their own side, and they're kind of lazy in that they're not very demanding towards their own reasons. However, when humans look at others' reasons, they are performing much better. They are unbiased. They even accept challenging reasons if these are strong enough, put forward sufficiently competently. And they're very demanding on the quality of these reasons. They would only be convinced by good enough reasons. So there is an obvious, in a sense, divide between how humans produce their own reasons and how they, behave with respect to reasons to others. They see this, in a sense, observation as what they call the nail in the coffin of the intellectualist approach, which is the intellectualist approach is very much the one based on the study of inference as in terms of a general and formal understanding of norms of good inference. This would include both, the kind of things that we do when we develop logic-based understandings of reasoning, but also more probabilistic forms of reasoning, including Bayesian reasoning. They also somewhat disagree, Mercier and Sperber disagree with the dual view of reasoning, of kind of type 1, type 2 kind of reasoning. In particular, they don't see reasoning as an alternative to kind of intuitive inference. They actually see it as a use of intuitive inferences about reasons. As I said, I'm not here to kind of advocate this view for human reason. There would be an interesting conversation to be had. But I'm interested, as I already said, on what this has got to say for us to design explainable AI solutions. And in particular, if you look at some of the things that Mercier and Sperber say, they can be quite inspiring for us doing explainable AI. They say people use reasons to explain or justify decisions already taken and belief already held in a kind of retrospective way. And then reasons play a role in the after-the-fact explanation and justification of our intuitions, not in the process of inference itself. I think we can actually focus on what they've got to say in terms of explanations, and maybe ask ourselves, should machines also use reasons to explain their output, independently of how these outputs are obtained? So we don't really care as to whether the machine reasons towards the output one way or another, but we could take this view to a kind of the AI in the automated AI direction, and use it to inspire solutions to explainable AI where reasons are explanations. So the explanations are built as reasons themselves. And we can go even further. We can, for example, see, given the push that Mercier and Sperber have given to the kind of dialogical form of reasons, or the conversational form of reasons, and in particular, they're pushed towards conversations where people can exchange arguments and counter-arguments. We can actually see this as somewhat an inspiration towards developing argumentative forms of explainable AI that lend themselves to supporting dialogues or conversations between humans and machines. And this is indeed what I'm going to try and convince you that can be done with the support of computational argumentation. Actually, the idea that argumentation can play a role in designing explainable AI can also be based on other work in the social sciences. Here I'm quoting some work from Antaki and Loider, that the majority of what look like causal attribution turn out to look like argumentative claim backings. This is about explaining in conversation and pushing for an argument model. And if you look at some of the work that already exists in explainable AI, such as LIME, you can see that there is an argumentative flavor to that already. So LIME, here I'm showing a LIME explanation for an input, which is the description of a mushroom, and an output, which is a kind of classification built, obtained from a model for predicting whether mushrooms are poisonous or edible. You can see that here there is a 100%, one probability one that the mushroom is poisonous, and the LIME explanation tells you the features that are responsible for that output, which can be seen as reasons or arguments for the prediction, and reasons an argument against the prediction that are, in other words, for the other output. So we can kind of see that there is already an argumentative flavor somewhat to some of the explainable AI solutions, in the particular, the feature attribution kind of approach. So I'm going to spend now a little bit of time to tell you something about computational argumentation before I can give you some an overview of some existing solutions to provide explainable AI methods that are based on computational argumentation, somewhat inspired, as I said, by the interactionist view of reasoning and other works in the social sciences. So in a nutshell, computational argumentation is about identifying argumentation frameworks, which are kind of abstractions of debates, and semantics for these argumentation frameworks, which are ways to evaluate these debates in such a way that one gets desirable properties. So, for example, which are kind of overall about the goodness of the semantics. So I'm going to tell you a little bit about one particular argumentation framework that is close to my heart. That's assumption-based argumentation. And in particular, looking at one instance of this general framework, which is what we call in a recent paper with Christiana Chiras and Quentin, forgotten his surname, on specific instance which we call Horn ABA, and then an instance of this Horn ABA which we call bipolar ABA, which is actually equivalent to another argumentation framework in the literature, bipolar argumentation by Cairol and Lagastier. And this bipolar kind of ABA is, like bipolar argumentation, is an extension, if you like, of the very well-known and influential abstract argumentation approach by Dung that most of you will be familiar with. Okay, so it's a bit of a path. We go from assumption-based argumentation all the way down to its instances. So assumption-based argumentation, ABA in short, sees frameworks as made of 4 elements. We have the component of a deductive system, the language, which is a set of sentences, and a set of inference rules. So this forms a deductive system, and it could be any. We enforce compactness, but otherwise it's anything you like. Some of the sentences in your language are singled out as candidate so-called assumptions. This set is anything, any subset of L of the language, but it needs to be non-empty. And then we have a way to disagree with these assumptions using a contrary mapping that associate to each assumption a single sentence in the language that is something that you need to prove, intuitively speaking, if you want to disagree with that assumption. So these are somewhat the building blocks of our arguing system from which debates can be extracted. And in particular, arguments end up being deductions supported by sets of assumptions. So we can say that the subset of the candidate sets of assumptions supports a certain conclusion claim if there is a deduction from that set of assumptions using the inference rules towards that conclusion. And then once we have arguments, we can single out attacks, disagreements between arguments. Argumentation is all about disagreement. So disagreement is an important concept within any argumentation framework. And we would say that an argument supported by set of assumptions A1 for conclusion C1 attacks an argument supported by set of assumptions A2 for claim C2, if and only if the claim of the first argument, C1, is the contrary of some of the assumptions in the support of the second argument. So as you can see, assumptions are the reason, are driving disagreement. To disagree with an argument, you need to disagree with an assumption that supports that argument. And arguments that are don't need any assumptions to draw their claims cannot be argued against. So these are somewhat the building blocks of ABA, and they are kind of what gives us ABA as a way to abstract debates. The debates are about arguments and disagreements between them. How are we going to evaluate these debates? As I said, semantics are a way to evaluate debates and determine sets of winning assumptions, which in ABA boil down to sets of winning arguments. And one can adopt several semantics, similarly to what happens in abstract argumentation that you may be more familiar with. Let's look at one such semantics, that's of stability. A set of assumptions is deemed to be stable if and only if, in the first place, it is what we call closed. Namely, it amounts to the sets of all assumptions that it kind of deduces. for which there is an argument from itself. So if you look at all possible subsets of these sets of assumptions and the arguments that can be built using rules in the didactic systems underpinning the ABA framework from these subsets, and you collect all the assumptions that can be derived from these arguments, then you want to end up with something which is not, going further than your starting point. So you want your set of assumptions to kind of contain everything you can get from it. And this is an important condition that only plays a role for the generic ABA setting and not necessarily for the kind of ABA settings that maybe you have heard more about, which we call flat. I am going to say more about this in a minute. So closeness is the first condition. Then the second condition, very important in argumentation, is that of conflict freeness. So you don't want to be able to build arguments against any assumptions in A, if A is a set of winning assumptions, because it would contain arguments that are in contradiction with themselves. So that's conflict freeness. And finally, and that will make what is crucial to the notion of stability and distinguish it from other semantics, is that there needs to be a way to disagree with every assumption which is not in the given set. So for every assumption outside the set, but still in your candidate pool of assumptions, there is an argument from your given set towards the contrary of that assumption which is outside. So you need to be able to argue with everything outside. So this is a well-known semantics, because as I will show in a minute, it kind of amounts to what conventionally in a lot of instances of ABA that correspond to existing non-monotonic logics. There are alternative semantics. One is set stability, which is defined in terms of the same closeness and conflict freeness conditions as stability, but also include a generalization, if you like, of the first condition, which is that you don't want to be able to attack just the assumptions outside the set. You want to be able to attack the closure of every set of assumptions that is outside. So here you need to enforce that condition, as I said, because we don't restrict ourselves to any specific sector of any specific ABA instance, and in general, in generic ABA, you may be able to draw assumptions from other assumptions, so that closeness is an important additional component. Okay, so this is just a light introduction to what ABA is, and there are some several instances of ABA that have been studied and have been shown to kind of instantiate ABA itself. I'm going to illustrate some of them with a very simple illustration, which is representing the presumption of innocence principle, that a person is innocent unless proven guilty. We know in KR that one could represent this information with in default logic that if X is a person and you can consistently assume that X is not guilty, then you would infer that X is innocent, and we might know that a specific person, Joe, is around, and be able to draw the conclusion, given this information only, that the person that that Joe is innocent. You can write the same principle in logic programming using negation as failure, and you could write it, for example, in non-monotonic logic using a belief operator, as well as in many other ways. And these approaches can all be seen as obtained as instances of ABA, where we choose different components, so different didactic systems and different sets of assumptions and different contraries. So, for example, in logic programming, we would say that the didactic system is the actual logic program itself. The language is the Hebron base, and the set of all negation failure atoms obtained from atoms in the Hebron base. The negation is failure are the assumptions, and the contrary of assumptions are what you would expect. And no matter which deductive system you use and which sets of assumptions and contrary, what we have shown is that the notion of stable extensions in ABA correspond to the standard semantics for for these logics, and all these specific instances here are can be seen to be flat. Namely, you can ignore any condition that has got to do about closeness, because every single set of assumptions is guaranteed to be closed, meaning that you cannot really infer any assumptions from other sets of assumptions. So in logic programming, for example, you won't be able to derive not of something from not of something else. You can only have not of something if you assume it. So flat instances are very important, as you can see that all these well-known instances are indeed flat, but there are non-flat ABA instances, which are quite important when we talk of explainability. In particular, we have recently defined with Christiana and Quentin the notion of Horn ABA framework, which is very simple and straightforward ABA framework, where the language is restricted to be just a set of atoms, and you have generic inference rules. So the restriction is on what the atoms are, and then assumptions and contraries will be anything you want. We have considered a special instance of these Horn ABA frameworks, which is basically one where the rules are real simple. Every rule is on the form a conclusion, a sentence S in L, so an atom, if a premise, which is an atom itself in L, because all the sentences in L are atoms, with restrictions as follows: that the premise A needs to be an assumption, and the conclusion S is either an assumption, or there exists some assumption whose contrary that S is. So this is a kind of very restricted form of Horn ABA framework, which in turn is a very restricted form of ABA framework. However, in general, those two, Horn ABA and bipolar ABA in particular, are not guaranteed to be flat, because assumptions can be inferred, and therefore sets of assumptions may not be closed. When we enforce flatness on bipolar ABA framework, we obtain Dung's abstract argumentation framework. But otherwise, we can have any form of argumentation. We can have also non-flat frameworks. Okay, so I don't want to spend too much time on this further, because I want to talk to you about kind of explainability. I want just to mention that amongst the properties that we consider when we study the goodness of the semantics are, of course, computational complexity properties, and this is a summary about some computational complexity properties we recently came up with. And you can see that Horn ABA, although simple, is not that simple in terms of computational complexity, and in particular is much more complex than the logic programming instance, for example. As I said, one important instance of bipolar ABA is of Horn ABA is bipolar ABA, which corresponds to bipolar argumentation. And I'm going to illustrate this with a very simple example, which is about some reasoning with some online reviews about a hotel. You might have 3 reviews. One says that the hotel is nice, has got a stunning spa. One review says I disagree, it's too small. And the third review says indeed the spa was something else. This is the kind of opinion you may find on TripAdvisor or Booking.com or wherever. And this can be seen as a bipolar argumentation framework of the kind that Tyrol and Baguette have proposed, where you have arguments that can be related using an attack relation or a support relation. And in formal terms, these here shown as a graph is just a triple consisting of arguments, an attack relation, and a support relation. Both are subsets of the arguments times argument set. And these are really bipolar ABA framework, as we have shown in this paper in PRIMA 2017. The particular representation of this bipolar argumentation framework under a particular interpretation of support is very simply illustrated here. Is one where the arguments and their contraries are part of the language. These are there are basically 6 atoms to care about here, and the set of inference rules say that A3, from A3 you can infer A1 because A3 supports A1, and A2 disagrees with A1, and therefore from A2 you can infer the contrary of A1. Here I'm abusing notation, and I'm using contrary as for defining sentences directly rather than giving it separately. So you can see that bipolar argumentation frameworks correspond to bipolar ABA framework, and actually we have considered other interpretations of support as studied in the literature in addition to deductive support that I'm illustrating here. So this is an important instance of ABA that we use extensively in providing explanations for other techniques, and it's important to notice that the abstraction that it affords is kind of useful and handy when it turns out to providing explanation for some other methods, ignoring how their reasoning is obtained and focusing solely on how the justifications are defined in terms of reasons, pretty much in the spirit of the interactionist view of reasoning. A final important ingredient from argumentation that is needed when doing explainability is the notion of gradual semantics. This is different from extension-based semantics that I've given you so far. So it's about identifying good sets of arguments, and instead about working with dialectical strength of arguments. And I'm running out of time, so I don't want to tell you too much about this. I want to point you to the fact that you can ascribe quantities to arguments drawn, for example, from votes. We call this base score, and you can define the semantics of arguments using the notion of dialectical strength, which is a mapping from arguments to a certain set of values, the interval 0, 1 here. And here I'm just giving you some numbers that come from applying an algorithm that we have defined with Antonio Pietro and others, Antonio Rago, Pietro Baroni, and others. I'm not going to give you the details, but this is an important notion, not that much the one we defined, but rather the fact that you can ascribe dialectical strength to arguments is an important notion. And properties that this dialectical strength has are also very important. And one that I'm going to focus on in the rest of the talk is dialectical monotonicity, which is about the fact that attacks decrease dialectical strength and supports increase dialectical strength. So finally, let's look at argumentative explainable AI, which is basically using a computational argumentation to provide explainable AI solutions for whatever. So we have a system that could be built from data, and we have outputs computing by these, by these systems. And what the vision of argumentative explainable AI is that we can extract argumentation frameworks from these, from which argumentative explanations can be drawn. And that's an important distinction. The argumentation framework is not the explanation, but is the basis from which the argumentative explanations can be drawn. In this recent survey, we have classified extensive work that already exists in this setting along various dimensions. In particular, we have identified 3 types of approaches, so-called intrinsic approaches, where argumentation is using by design, in a sense. This is somewhat in the spirit of building interpretable models. We use argumentation for building models, or others use argumentation for building models. And that's one way to provide explainable AI by computational argumentation. But there are other ways, in particular post hoc way, which are obtained from, where argumentation frameworks are obtained from non-argumentative models. And the frameworks may provide complete or approximate representations of the explained model. Now, something which is very important is that the intrinsic approaches will choose a semantics, for example, stable semantics or set-stable semantics, or a gradual semantics. But post hoc approaches cannot choose. They need to inherit the semantics from the underlying method, because otherwise they will not be explaining the method. So if you want the explanations to be faithful to the methods, you need to look at what the method does, rather than choosing an arbitrary argumentation semantics. So I'm going to give you an example of an intrinsic method very quickly, and then an example of a post hoc method. As an example of intrinsic approach, I'm going to tell you a little bit about some recent work we've been doing in the context of the Road to H project that Ezra mentioned in her introduction, I've been involved in, which is about identifying, supporting reasoning with clinical guidelines when patients have multiple morbidities, and therefore there may be lots of interactions between guidelines, and in particular conflicts between guidelines about different diseases, and these conflicts need to be resolved for the patients to be treated. So what we use in this work, we start from a conceptualization of guidelines by Zambolini et al., which is really taken from within, if you like, the semantic web realm. This is about kind of identifying recommendations for treatments based on information that is captured in the guideline. Here I am giving you just a simple example, which is taken from Zambolini et al. As to two recommendations to administer a type of treatment. This should be administered according to the first guideline, but should not be administered, but another treatment should not be administered according to another guideline. And what happens is that the second treatment, aspirin, is actually a special case of the first treatment, unsaid. I don't have time to go into details, but there is this conceptualization, and what we have done is providing an automated mapping between this conceptualization and an extension of the kind of other framework I have given to you, where in addition to the deductive systems, assumptions, and contraries, we also have preferences over assumptions. We have goals and priorities over goals, where the preferences take into account patients' needs, and the priorities between goals take into account clinicians' expertise. So this particular setting here will be represented by a bunch of rules. You can see that recommendations amount to assumptions that can be argued against. We have information about the specific patient we are applying this to. This may be taken automatically from electronic health records. And then we may have patients' preferences over specific kind of recommendations, and priorities over goals. And pretty much in the ABBA style, with extensions as set of winning assumptions, we come up with recommendations that somewhat amount to avoiding conflicts, resolving conflicts, and interaction. As I said, I don't have the kind of time to go into details, but this is an example of a method which is interpretable and natively uses argumentation at its heart. Another example I want to give you is of an approximate system where the semantics is not chosen, but is inherited from the underlying system. And in particular, I'm focusing here on explaining a convolutional neural network for text classification, for example. This is a very simple one with just one hidden layer. I don't have time to go too much into detail, but this is one of the, although albeit simple, is one of the kind of black boxes approaches that one may want to explain. And we focus on explaining its functioning with a view to developers understanding what it does and get information about debugging this kind of method if it doesn't do what it's supposed to be doing. And what we can do is using as gradual semantics for a bipolar argumentation framework, something drawn from the network, for example, activations, or an existing explanation method, which is layer-wise relevance propagation. So treating these numbers basically as a semantics and guaranteeing dialectical monotonicity property satisfaction, we can obtain an argumentation framework where we have support and attack between arguments that can be input words or classifications or filters that are within the system itself. We don't just focus on extracting argumentation frameworks for explaining models overall and conclusions from the models, but we also work on argumentation frameworks that are providing local feature attribution-based explanations, such as with our recent work on Bayesian classifiers that Emanuele Albini will present at QuickEye next week. So I'm not going to give you much details about that. All in all, this is about extracting argumentation frameworks, but of course it's very important that we also have ways to extract argumentative explanations. And here the interactionist view of reasoning can come handy by forcing us towards a view of explanations that is interactive. For this particular work, for example, we have extracted visualizations, if you like, of the underlying argumentation framework, where we show filters indicated here in the middle layer as word clouds, and visualizing the strength of arguments appropriately in a way that allows users to interact with the argumentation graph. In other work, we look at explanation as dispute between a proponent and opponent, whereby given, for example, an abstract argumentation framework and wanted to explain why a certain output A is computed, we can build disputes between a proponent and an opponent to illustrate how the conclusion came about. And in other work, we use the argumentation framework as a basis for driving conversations using templates. For example, given bipolar argumentation frameworks drawn from a recommended system that we built from reviews on Rotten Tomatoes, we can build automatically conversations with users. If the user asks why a certain movie was highly rated, we can then look at the argumentation framework and identify, for example, stronger supporter and attacker, and generate automatically using templates answers to the user queries. And we can drive a conversation whereby we navigate the argumentation framework, providing more and more information all the way down to the sources of the information, which is the reviews. So this is something we automatically extract from the reviews, and the numbers here, which are from an argumentation viewpoint, the dialectical strength of the argumentation framework, are really driven by the recommended system itself. So we choose those numbers as our dialectical strength. Okay, so a bit of a rush towards the end, but I hope I have convinced you that computational argumentation can empower various forms of XAI in the spirit of the interactionist view of reasoning. As Ezra said, I'm supported in this research by a bunch of general standards, and I'm actually recruiting for some of it. So if you're interested, please get in touch with me. There are lots of questions that are still open. There is a lot more work to do, especially for explaining Blackbox models. There is the aspect of debugging driven by argumentation that needs extensive explaining. If we want to have conversations, we should aim at getting free ones in a constrained natural language. There is work to do with natural language processing experts to come up with that. We need to evaluate our explanations. We need to maybe use more from computational argumentation to get better explanations. And then overall, a lot of this is about engineering, but ideally we would want a scientific theory of argumentative explanation. This concludes my talk. I thank you for your attention.